Okay, so welcome back. So we are in the process of proving that H10 omega is precisely the subspace of H1 omega of those functions whose traces are 0. Okay. So, now we just proved these two inequalities for C1 omega functions which are C1 in omega bar, but we have already learned that C1 omega bar is dense in H1 omega, and since we are only using integrals here, okay, so this also valid. So, valid for f in H1 omega by density. So, you can take a sequence in C1 omega bar converging to f, and then you pass to the limit. Okay. So, this is what I was referring to. So, this is starting with a small piece gamma 0. So, we okay, I forgot to tell what is this x. So, this x delta is x prime phi x prime plus delta. So, this sits on gamma delta, and x 0 the surface we started with. So, starting with a small simple piece, okay, and then getting a parallel simple piece. So, these are essentially traces, right, on. So, this is trace on that gamma delta, and this is trace on gamma 0, and we are getting a kind of this estimate. Okay. So, this is the continuity I was referring to. Okay. And now okay, so they express continuity of traces. So, these are traces. Okay. Okay. Now, suppose, okay, so that is next thing. Okay. Now, suppose f restricted to gamma 0. So, this is nothing but trace of f on gamma 0 is 0. Okay. So, then we get, so this is 0. So, one of the term is 0, right, one of the this f x 0 is 0. Okay. So, then we obtain this f L2 gamma delta. Okay. So, square is there. Okay, let me put that square. C square delta f H1 q delta square. Okay. So, now for example, we can take, so this again technical thing. So, you can fix this 0 delta some less than or equal to some rho rho 0, and so you fix rho 0 such that this q rho 0 is in omega. Okay. So, I am just omitting that. Okay. So, what we can get is, so this this if you do all that analysis, so this f of, let me write in one go, okay, this omega rho, let me simply write that O of rho as rho tends to 0 plus. Okay, so meaning of this again, okay, so this something more. So, okay, provided, okay, so that you remember that gamma 0 is 0, the trace is 0. So, this means f this L2 norm, okay, so divided by rho, so that is important, also tends to 0 as rho tends to 0. Okay, so this, okay, so I have skipped many steps here, but the idea, I am just providing idea. So, let me just say this in okay, so thus what we have shown is, thus we have proved that if f is in H1 omega and f gamma 0, remember this gamma 0 is a simple piece, a trace is 0, and this q, okay, sorry, just notation, okay, so this is not q, I am using q. Okay. Q rho. So, q rho is the region between those two parallel surfaces, small pieces. Okay. Q rho is contained in omega, then this f L2 q rho is little of, okay. So, this is the important observation, and we have made use of this vanishing of the trace. Okay. So, now one more lemma, I will not again prove it completely, but lemma I will just. So, if f is in H1 omega and trace is 0, then norm of f L2 omega minus omega delta is little o of delta. So, I will just mention this. So, again this is small o. Okay. So, when you divide by so, if you want to write in terms of epsilon and delta, so this means given epsilon positive, there is delta that depends on epsilon, such that f of this L2 norm omega delta is less than delta epsilon. Okay. So, after dividing by delta it goes to 0. Okay. So, this is the meaning of that. And of course, this is only for L2 norm. So, this we cannot expect for the gradient norm. Okay. That we will see that. So, what is this omega delta? Omega delta is set of all x in omega which are away from the boundary by delta. Okay. So, delta is small. Okay. So, for example, if we take so this is omega. Okay. So, this is almost if so just concentric circles spheres. So, this is omega delta and this distance is delta. Okay. So, for example, if you take omega a ball of radius r and omega delta is ball with radius delta. So, the measure of omega minus omega delta. Okay. So, measure, let me write measure or volume. Okay. So, this is order of delta. Okay. So, that you can just so here also we can expect the same thing. So, that is it will be order of delta and obviously that goes to 0 as delta goes to 0, right, no problem. So, this measure of this omega, this region omega minus omega delta can be made as small as we please. Okay. And then the absolute continuity of the integral. Okay. So, say that this integral can be made small, but here something more. Okay. So, that absolute continuity of the integral only gives less than epsilon, but not delta epsilon. Okay. So, however, for gradient norms, so by absolute continuity of the integral. So, you just refer to your measure and integration, continuity of the integral we can assert this norm of gradient. Okay. L2 omega minus omega delta is less than epsilon if delta is small. Okay. So, this measure will be small. So, this then you can. Okay. But here this additional condition that trace is 0, we are getting little o. Okay. And now the analysis of this thing I will not elaborate that thing. So, you take any piece, simple piece gamma 0 here, okay, and do the previous analysis, that continuity of the trace, okay, and then you can get that estimate, and finally, so you have to use the compactness and then you join together all the simple pieces. Okay. So, this is very technical, but just notice that the analysis here is taking place near the boundary. Okay. So, we are taking a big portion out of omega, only a small portion is remaining here, and that omega minus omega delta region very much looks like this q delta q rho rather. Okay. So, it is between two parallel surfaces. So, here one is the boundary itself and another one this boundary of the this omega delta. Okay. So, this analysis gives us this important thing. Okay. And now, using this lemma we complete the proof of the theorem. So, that is so it is a rough sketch, but you can find more details in any book. They are very technical. So, one has to sit down and do all the computations. Proof of the theorem, that characterization of the H1 omega. Okay. So, suppose f is in H1 omega and trace is 0. So, remember the smoothness of the boundary. Okay. So, we know that this C1 omega bar is dense in H1 omega. Okay. So, pick some delta epsilon positive, arbitrary, pick epsilon positive, then there exists delta that depends on such that f in this L2 omega minus omega delta is less than delta epsilon. Okay. So, this is from the lemma. And the gradient norm. Okay. So, you can put together. So, no harm there. So, H1 omega minus omega delta is less than epsilon. So, this is absolute continuity of the integral. Okay. So, the first one follows from the lemma and this is the absolute continuity of the integral. Okay. And this is where we have used the hypothesis that trace is 0. So, remember that. Okay. And that is where that delta is coming, extra delta. Okay. So, choose, so this is by density, choose some f n. So, again this n depends on the sequence we are choosing. So, n again depends on this n epsilon, okay, that is such that f minus f n so you write the, so this is by density. So, let me just write that. Okay. So, f n again I take L2 omega minus omega delta. Okay. So, f n is close to f and for f we have obtained this estimate. So, let me just write that. delta epsilon. So, lemma plus estimate for the f. Okay. And this again comes from the absolute continuity of the integral. So, this is h1 omega delta. So, this is absolute continuity. The proof would have been over if this Fn had compact support. Okay. So, that is not assured here. So, density result just gives us C1 omega bar. Okay. And again this is a standard technique. So, you take this Fn and use a cutoff function, okay, to make it function with compact support. Okay. So, here is, so put, so again you are seeing this modifiers zeta delta x. Okay. So, this omega delta by 2. Okay. So, we are still going inside there. So, this rho, okay, so rho we are using that modifier sequence delta by 3, this x minus y dy. So, this is modifiers. Okay. So, this is nothing but your characteristic function of this region omega delta by 2 star rho delta by 3. Okay. So, how useful they are, right. So, then okay, that implies j delta is C infinity. Okay. Let me write that. So, j delta of x is 1 for omega 5 delta by 6. Okay. So, these are crucial because we want this to be in omega delta. Okay. So, we can fix some other coefficient there, that is not important, but finally it has to be 1 in this omega delta, and j delta of x is 0 for x not in omega something delta by 6. And of course, 0, this is from the very okay. So, important thing is this j delta has compact support. Okay. So, now what we have to do is, okay, so just consider this, okay. Consider this Fn j delta by 3. Okay. So, this is C1C. Okay. So, that is in, so finally we have obtained a C1 function with compact support, because j delta 3 has compact support. And now first you approximate this Fn with this, okay, in various norms L2, H1, etc. Okay. And finally, you obtain this F minus Fn j delta by 3. So, by triangle inequality, so this H1 omega is less than or equal f minus fn plus fn minus fn j delta by 3. Okay. So, this is already under control. So, this is some less than epsilon, and here also you get some constant, you may get some epsilon. So, the whole thing is, so 1 plus c epsilon, and that shows. So, and this has compact support. Okay. So, this is in C1 C omega. So, that f in H1 omega whose trace is 0, we are finally able to approximate it by C1 function with compact support in H1 norm, and that completes the proof. Okay. Proof is hard and technical. Okay. So, not just hard, but it is okay. So, with this we come to an end of this discussion on Sobolev spaces. We have covered many essential topics that will be used in the second part of this course. Even with all this what we have done, if we require little more from this theory of Sobolev spaces, we will do that when we in the second part of this course. Thank you.